Welcome to the next lecture. We will continue solving the boundary conditions. I will again recall what is the uh, model we are studying right now. We have here a boundary, a surface between medium 1 and medium 2. Medium 1 can be suppose free space, medium 2 can be suppose some metal, and medium 1 has permittivity given as mu1 epsilon 1 and medium 2 as mu2 epsilon 2. So as we can see, when an incident wave is impingent on the surface, it gets partly transmitted and partly reflected. This is usually case with electromagnetic waves, and even in sound waves you observe this effect in various cases of surfaces, that whenever you emit some audio or any sound, and part of it may get reflected, part of it may get passed up. Even with light, you might have observed if there is some glass material which is not fully mirror type, part of the light gets passed and part of the light gets reflected also. Okay, now we know that the solution of wave equation, which we derived in the last class based on our previous analysis of wave equations, it was of this form: e to the power j omega t minus beta z, which is the electric field component along the axis, and then the magnetic field component we assumed is along the y-axis, and that is given over root over epsilon naught b nu naught ex. And of course it is a transverse electromagnetic wave, hence the propagation direction is along the z-axis. So that is what I have drawn here. So this is the z-axis. So electromagnetic component, magnetic field component will be on the direction. This is the y-axis. Z will be the direction of propagation. Y is the direction of electric field, magnetic field component, and electric field I have we draw it here like cross. It actually means it goes into the page, okay, into the screen, perpendicular to both y and z. Now we would like to study how the waves get transmitted and reflected and what is its effect. So for that we will first fix the reference frame for time. See, we are considering here the moment wave is getting reflected or transmitted while it strikes the surface. Okay, so we fix that time as, suppose we take that time as t is equal to 0. Then your wave equation at that time t is equal to 0 will become e naught e to the power minus j beta c. Okay, because we are considering particular time frame when it gets reflected as well as transmitted at the surface. We fix that time as t is equal to 0. Okay, now what will happen is, what is the effect of reflection and as well as effect of the incident wave getting passed through, is that you see this z, we are here writing z because this wave gets propagated in the direction of z. What will be the reflected part of reflected wave component? That will be definitely e to the power plus j beta z, because the reflected part, see, you are taking the plus z direction in this way, so the reflected part will be in this direction minus z. So minus z, if you change here, it becomes plus z. So this is the reflected wave component. So in medium 1, the total net field will be so I will write here net electric field. It will be equal to the incident wave plus reflected wave. Okay, incident plus reflected wave. Now, how much will be reflected? Suppose I will give example of light. Don't take it directly compare with light, but I am giving an example. Suppose there is a surface like mirror where there is a perfect reflection. Okay, so what will happen in that case? In that case you will have exactly, if the incident wave is e naught e to the power minus j beta 1 z, the reflected part will be e naught e to the power j beta 1 z. So I'm writing here beta 1 for medium 1. Okay, so we'll have for medium 2 we'll have different beta. Recall that what beta depends on. Recall, here is a previous lecture slide, so see what beta depends on. Okay, beta depends upon the omega, which is fixed here, and it depends upon mu naught and epsilon naught. So if any medium has different mu naught, different epsilon naught, for that medium this beta will be different. Okay, so I will write beta 1 for medium 1, which has permeability and permittivity given by epsilon 1 and mu 1, and for medium 2 I will take beta 2. Okay, this is our notation, beta 1 beta 2. Now it is a perfect reflection case, and there is another case. Suppose it is you are passing a light through a glass where there is no reflection at all. So in that case, when the incident wave is this, the reflected wave will be 0. And then there are in between cases. There is a surface which partly reflects the light. So what I will write is that reflected part we can write as reflected wave as some gamma times, okay, e naught e to the power j beta 1 z. So for gamma is equal to 1 means perfect reflection. Okay, gamma 1 perfect reflection, and for gamma equal to 0 will mean no reflection at all. Okay, this is the reflection part. So what will be the net electric field? I will denote that as ex1. 1 means that it is medium 1. Okay, will be equal to the incident wave e naught e to the power minus j beta 1 z plus the reflected wave gamma times e naught e to the power plus times j beta 1 z, which we write in short. Okay, I recall here again, beta 1 is equal to under root of omega times under root of mu 1 epsilon 1, and we also have intrinsic wave impedance as defined in last lecture, which is denoted by eta 1 equal to mu 1 by epsilon 1. Okay, we can also write this in terms of eta naught. What is eta naught? Eta naught is mu naught by epsilon naught. Okay, it is for the free space. So we can write also eta 1 as eta naught divided by under root of epsilon r1, which is the relative permeability. Okay, this you can easily see by using definition of this relative permeability. And gamma is called reflection coefficient. And meanwhile we can also write hy1. So if you recall from this what I wrote here at the top, I wrote, if we derived it last time, hy, which is the magnetic field intensity component, is equal to root of epsilon naught by mu naught times ex. Or you can also write it as, since epsilon naught mu naught is denoted as eta 1, you can also write hy1 is equal to electric field component divided by the intrinsic wave impedance, which I defined here. Okay, so which we can write in detail as e naught divided by eta 1, this equation. Okay, this is the magnetic field in medium 1. Now let's go to medium 2. In medium 2 there are only transmitted waves. Okay, so how we will denote that? See, suppose there is a perfect reflection, okay, like a mirror. So what will be the reflected wave? That will be 0. Okay, so in case of, right, and similarly in case of in the case, suppose a glass wherein there is no reflection at all. So the transmitted wave will be exactly the incident wave. Okay, so we have here one more coefficient, like we had a reflection coefficient. We have something called transmission coefficient. I defined by t is equal to transmission coefficient, and I can write electric field component in medium 2 is E naught t times e to the power minus j. Now beta 2z, because we are in medium 2, for medium 2 we have beta 2, which is given by omega under root of mu 2 epsilon 2. And similarly magnetic field component can be written as, okay, where this eta 2 is defined as, it is intrinsic wave impedance of medium 2, okay, as this is defined for the previous case, and t is the transmission coefficient. Okay, now for the continuity of wave at boundary condition, so I write here for continuity of wave impedance at the boundary, we need that the wave impedance is to remain the same. Wave impedance is same as it is for medium 1 and as it is for medium 2. Okay, so we denote the wave impedance as zz as a ratio of electric field component at medium 1 divided by magnetic field component, okay, computed at z is equal to 0. So this is the wave impedance at boundary, okay, at boundary. Okay, now so this is your diagram which we are considering. So this point we are taking as z is equal to 0, this point, the boundary point. Okay, so far so good. Now we want that what will be the wave impedance at boundary considering medium 2, that will be ex2 divided by ये होगी impedance at surface 2, sorry, medium 2, right? I have taken ex2 hy2. Okay, so these two should be equal. That is the boundary condition. These two should be equal. Now we know the ratio ex1 divided by hy1. What is it equal to? It is equal to this, right? And at z is equal to 0, this is equal to, it becomes e naught cancel, eta 1 times 1 plus gamma divided by 1 minus gamma, right? Similarly, what will be the ratio of electric field and magnetic field in medium 2 at z is equal to 0? So e naught cancel, and I think all the terms get cancelled, and it becomes simply eta 2. So for continuity, we want these two impedances to be same. So continuity implies that eta 1 times 1 plus gamma divided by 1 minus gamma is equal to eta 2. From this equation we can get directly gamma also as eta 2 minus eta 1 divided by eta 2 plus eta 1. So this is one thing we got. And now we also have one more boundary condition, that the tangential components of electric field intensity are continuous across the interface. So what does that mean? It means that the electric field component at z is equal to 0 should be same as electric field component in medium 2 at z is equal to 0, right? Now you can easily see at z is equal to 0, it was e naught divided by times 1 plus gamma should be equal to, this will be e naught times t. Very simple calculations. So it means transmission coefficient should be 1 plus reflection coefficient, which can be also written as twice eta 2 divided by eta 2 plus eta 1. And in particular, if medium 1 is lossless dielectric, that is sigma is 0, conductivity is 0, just like vacuum or free space, then we define a ratio which is called standing wave ratio as the maximum value of electric field divided by the minimum value of electric field. So I will write it as magnitude of E max 1 divided by E minimum 1. Okay, now let's find what the quantities will be. We know how E max is defined. E1 is defined. E1 of x, sorry, Ex of 1 is, to find its maximum and minimum value, I have written here something. I will tell you what it means. You denote this beta 1z as theta. Okay, so how can we write this? Is then e to the power minus j theta plus gamma e to the power j theta. Okay, and e to the power minus j theta I can write as cos theta minus j sin theta. E to the power j theta I can write as cos theta plus j sin theta. Okay, so this is the Ex, and mod of Ex1 then can be written as real square plus imaginary part square. Okay, so if you see, I will combine here the real and imaginary. So real part is cos theta into 1 plus t, imaginary part is sin theta into t minus 1. So we know that mod is real square plus imaginary square, and I will write in terms of cos, so it becomes cos square theta times 1 plus t whole square minus 1 minus t whole square plus sorry, it is not t, it is gamma, sorry. Okay, now when will this take maximum value? Maximum value will correspond to here for theta equal to 0, because in that case cos has maximum value at theta equal to 0. So in that case we will get Ex, I will write here max is equal to mod of Ex1 at theta equal to 0, which is under root of 1 plus t square minus 1 minus t square plus, sorry, it's gamma, I was saying again t, gamma minus 1 minus gamma square. So this gets cancelled, and since gamma is always between 0 and 1, so it becomes 1 plus gamma. Okay, similarly the minimum value will be the minimum value of electric field for theta equal to pi by 2. We know that cos is magnitude of cos, it is a cos square theta. Cos square theta is minimum at pi by 2 and its value is 0, and it becomes under root of 1 minus gamma square, which is 1 minus gamma. Okay, so standing wave ratio will then become 1 plus gamma divided by 1 minus gamma. This has important significance in waveguides, we'll see it later. And now we can use what we have already studied as the Poynting vector in Poynting theorem, that what is a power density transmitted across the boundary. That is given by that Poynting theorem, that we have derived that it is half electric field component times the conjugate of magnetic field component, right, at z is equal to 0, which is boundary, dot product with the z direction, right. Okay, so we can now easily compute it. We know that electric field here, okay, has only one component, Ex, in the direction of x, so Ux. Okay, and magnetic field has only one component in the direction of y, right. So E cross H star. Now I will write here H star directly, that is the conjugate, we'll take a conjugate later, will be Ux, Uy, Uz, then, right. So as you can see that Ux part is 0, Uy part is 0, only it will be equal to Ex Hy conjugate Uz. Okay, and P transmitted will be half Ex Hy conjugate Uz dot Uz. They are in same direction, so half Ex Hy conjugate. Okay. Now we are considering it at boundary z is equal to 0. So we can take either. So Ex 1, suppose if we take at z equal to 0, that is equal to E naught into e to the power minus j beta 1z plus gamma e to the power j beta 1z at z equal to 0. So at z equal to 0, it is E naught times 1 plus gamma, and Hy, you know, that is simply at z equal to 0, that will be equal to Ex1 divided by eta naught. Eta 1. Okay, eta 1. Okay, and that will be at z equal to 0. So that will be E naught times. Okay, no, we have to take a conjugate. Okay, let me first write H1. So Hy1 is equal to E naught by eta 1 e to the power. Now, oh, it is actually here minus. I think I need to tell that beforehand also. I have written here, if you see, minus, this minus gamma, right? Whereas here it is plus. The reason for this is that since the direction of propagation we want to keep same. Okay, what does it mean is this. So before reflection, let me write here, before reflection, what was the direction of electric field? Ux, right? And what was the direction of magnetic field? Uy. And to get direction of the wave, you need to take cross product, because it is the direction of electromagnetic waves is at the cross product of E and H, right? This E cross H. Now you know that Ux cross Uy is Uz. Now because of reflection, the direction is minus Uz. Okay, and you see, we are, for electric field component, we are changing this here, z to minus z, but magnetic field component is gamma, we are taking it positive, so direction of electric field remains Ux only. If direction of magnetic field is also taken as Uy, then it means that even after reflection, the direction is Uz. But we know that reflection will change direction, it will be minus of Uz. For that purpose, one of the component has to change direction, the sign also. That is why minus Uy direction should be for magnetic field. Hence, instead of plus gamma, for magnetic field we write minus gamma. Okay, that is very important. Now I will come back to the equation I wrote just now. So initially I wrote wrong here. It is now here. It's actually minus of this. Okay. Now this is Hy. Okay. And what will be Hy1 conjugate? That will be E naught by eta 1 e to the power, this will become j beta 1z minus gamma e to the power minus j beta 1z, and at z equal to 0, it will be equal to E naught divided by eta 1 times 1 minus gamma. Okay, now power transmitted will be equal to half E naught into 1 plus gamma times E naught by eta 1 into 1 minus gamma, which is E naught square 1 minus gamma square divided by twice eta 1. I can reframe it in this way. Suppose if we see what is this eta naught square divided by twice eta 1, this is the incident power, right? You can easily check it. This is the incident power at z is equal to 0. So I can write P transmit is P incident times 1 minus gamma square. Now I can also write it in this way, P incident minus P incident gamma square. This part is easily, we can see it is a reflected power, PREF. So we can see that power transmitted is power incident minus power reflected, and we have the closed form expressions for all of them. This was a case where we have normal incidence, perpendicular. We also have oblique incidence. We will see that later on. But this reflection phenomena we just studied, you will see it will be repeatedly using in waveguides. So this much for this lecture, and we'll continue with the further discussions which will lead us to the analysis of propagation of EM waves through waveguides. Thank you.